All right, hello everyone. Today we have kind of a tough job to do. Today we have to talk about what I think is probably the most difficult remaining concept in the course. And that's not to say it's impossible. Most people do fine with it. It's just usually it takes a little bit of time for this sort of matter to sink in, a couple points especially. And so doing it remotely will probably be even a little bit more challenging, so make sure you're paying attention to this one. We're talking about electric fields today, okay, electric fields. Now, to start talking about electric fields, we gotta go back and talk about the electrostatic force. I know it says electromagnetic there, sorry. It really, electromagnetic is the right word, but I know you guys are used to electrostatic. We're gonna talk about that in the gravitational force. These forces are different from other forces that we've examined. If you think about applied force, or tension, or spring force, or normal force, or any other force that we've talked about, all those forces require two objects to actually be touching. The gravitational and electromagnetic, or for you guys electrostatic right now, those forces do not. They do not require objects to be touching. This should seem really weird to you. Forces are pushes or pulls. Every other force you've talked about happens because two objects are in contact. How come these forces are different? Why do they get this special permission to act at a distance? Okay? The force of gravity, as you know, is caused by objects that have mass, and the electrostatic force is caused by objects that have electric charge. We should be used to that at this point. The reason that these forces work the way they do is because mass and charge have this weird property where they very literally change the space around them. You've heard of the word warp before, like a piece of wood gets warped. What that means is it starts to bend in ways that it wasn't supposed to, okay? It kind of settles into a weird position. That is what mass and electric charge do to space. It warps the space. Now, this is the part where I usually start sounding like a hippie, like, whoa, it totally changes the space, man. I'm dead serious. This is what happens. The mass and the charge literally, quite literally, change the space around them. Now, for most normal objects, we don't really notice this, or it's so common that we don't even think about it, okay? But what I'm saying is the space, the three-dimensional space around an object that has either mass or charge physically gets changed. And this is not something that's unusual. This happens for every object that has mass and charge. We have a name for this warping or changing of the space that changes how objects move. In physics terms, when you change the space around some object, what you say is that object creates a field around itself. We could have spent some time talking about gravitational fields, and we did mention it very quickly. We did say gravitational field strength as a synonym for acceleration due to gravity. But we don't talk about that much because, you know, back in November, December, when we talk about that, your brains are not ready for the idea of fields. Now they are. Now we have to talk about fields. An electric field definition is the alteration of space created by an electric charge. Now you might be wondering, okay, why do we have to talk about this? We just talked about the force. Why do we have to talk about this weird field thing that seems like it's totally made up or out of Star Wars or Star Trek or something? Well, the reason being the electrostatic force equation that you just learned it's useful, but it's only useful in some certain cases. It's useful, remember, when we have spherically symmetric charge distributions. That means charges that are either spheres or point charges that we can approximate as spheres. Imagine you just had like I don't know, like a line of charge or like a rectangle of charge. We couldn't really use that equation. At least we couldn't use that equation very simply, okay? We would have to do some very complex mathematics with it in order to get the right answer. Instead, what we typically do is we determine the electric field at points surrounding some distribution of charge. And it's kind of like a backdoor way to finding the electrostatic force, the electrostatic force on an object. if we measure the electric field, which again is also kind of complex in how to do it if you're doing this in the field. We're going to look at some pretty simple electric field distributions. We can determine how other charges would react to that field. In other words, how much force they have put on them. What we're really doing when we talk about electric field is kind of mapping the area around some distribution of charge so that if we were to bring other charges in, we would know exactly how much force they would be under. Okay, that's the idea with electric fields. We are essentially, we're saving a little bit of time by not just calculating every single force possible, by making a map around a distribution of charge that shows, okay, if I put in some more charge here, how would it respond? That's why we talk about electric fields. We represent electric fields with vectors. This is a vector quantity. And the vectors have a special name. They are called electric field lines. Okay? To measure the magnitude and direction of electric fields, we basically do what's called a thought experiment. We use what's called a test charge. A test charge is basically an imaginary little particle. Imagine like a proton, okay? Usually a test charge is a proton. A small amount of charge that does not affect the field itself. The field is already generated. We put a test charge in, a very small charge like a proton, and we imagine what would happen to that proton in different situations. So I'm going to show you, for very simple charge distributions, how an electric field would look. Electric fields near positive and negative point charges. So these are two different examples. So here's how you use the idea of a test charge to figure out, okay, well, what would the electric field look like? Here's a positive test charge. Imagine we were to put a little proton right here. I'm not going to draw it, but like right here. In which way would that, here's what you think to yourself, in which way would that proton experience a force? Okay, you have a giant positive charge right here and a little tiny proton right here. Those two are going to repel, right? The proton is going to experience a force upwards. So what we would do is we would draw an electric field line starting from our charge. It always has to start directly on the charge, no gaps. And we draw a vector up like this. Okay? Same thing if we put the proton on the right-hand side. The proton and this big positive charge would repel away. So we draw a field line that represents the direction that the proton would feel a force if it were placed at that point. Okay? If you are confused by that wording, go back and listen to it again. That's pretty much the simplest I can put it. The direction of the electric field line is the same direction as the direction of the electrostatic force that would act on my test charge if I were to put it at a certain location. If I were to put the proton down here, the proton would be repelled downward. If I were to put it here, it would be repelled to the left. I think you've probably got the pattern now. For a positive distribution of charge, spherical, like this, the electric field lines simply point straight out and away from our positive charge. So what this is supposed to show you is it gives you an idea of if you were to put a proton at any point near this other big positive charge, if you were to put a test charge in here, the electric field shows you the direction that the force on that proton would be in. Okay? So for a positive distribution of charge, like this, spherical, we just simply have a it's just electric field lines going straight away. Okay? Radially outward, we would describe that as. What about for a negative charge? What if I were to put a proton right above this negative charge right here? Well, the proton would be attracted to it, right? It would go in towards the negative charge? Absolutely. Matter of fact, that would be true even if it was up here. it would be attracted in like this. It would experience a force downward towards the charge. So, for a negative charge, we end our electric field line on the charge itself. If the proton was over here, it would experience a force in like this. And I think you get the point here. At any point, the proton would be attracted to our negative charge, and the force would draw it in. So our electric field lines all point inward. Pretty simple, right? These are very simple distributions of charge, but electric fields look pretty simple. Now, if you were to guess, where is the electric field for this object going to be, or for this charge, either of these charge distributions, where is it going to be the strongest? If you guessed close to the charge, you're right. Closest to the charge. Now here's another question. Where are the field lines closest together? Where do you have to travel? If you were like going around this, where do you have to travel the least amount of distance in order to hit another field line and another and another? Also closest to the charge. The field lines are kind of spread out here. They're much closer together in here. So that's kind of interesting, because what do you think this tells you? If the field is strongest closest to the charge, and that's also where the lines are closest together, what do you think the closeness of field lines tells you? This is what tells you how strong the electric field is. How strong that alteration of space is that can affect other charges. So what that means is the electric field is stronger closer in, which ultimately means that there's going to be charges that are more affected when they're closer in than when they're farther away. And again, how are they affected? They get a force put on them, okay, the electrostatic force. Notice, though, that I don't even need to have another charge in here in order to have an electric field. This electric field for this positive charge, or this electric field for this negative charge, exists without any other charges present. Forces, electrostatic force, does not exist unless you have two charges. Electric fields exist as soon as you have charge. Charges automatically alter the space around them. Let's go to the back. Okay. So, here's what field lines don't show you. These are some common misconceptions. Field lines do not show the path of the test charge. They don't show the path that a test charge would take in all circumstances, okay? Sometimes people think that that means if you just put a test charge here, it'll go zoop and go right into the charge. That's not true. What if you put that charge there, but then you also kind of pushed it to the right? It would kind of go like this. That's not the direction the path that the electric field line points. So the direction does not show the velocity of a test charge. It does not show the path it takes. It points in the direction that the electrostatic force on that test charge would point. So the electric field line and the electrostatic force should always point in the same direction. Okay? If you put a charge up here, the electric field points in, that's the direction that the object will experience a force. That doesn't mean it's going to go in that direction. That just means that's the direction it will experience a force in. So again, they only show the direction of the electrostatic force at a location. In addition, the length of field lines has nothing to do with their strength. Okay? The length of these field lines has zero to do with their strength. I could have drawn them this big. Okay? I like to draw them big just because I've got lots of space on that paper to take up. But the length means nothing. Okay? The length means absolutely nothing. The closeness together tells you about the strength. The direction tells you the direction of the field at that point. Other than that, that's it. One more thing before I go for this first video. Field lines will always start on positive charges, and they will always end on negative charges. End meaning that's where the head goes, start meaning that's where the tail goes. You can see this right here, okay? They start on positives, they end on negatives. Now, If you only have a charge like this, just positives or negative, just positive or just negative, and we'll see more cases like this, yeah, they can go out to infinity, but they have to start directly on it. If they don't, you're going to lose credit. If it's going to a negative, they have to end directly on it. If they don't, you're going to lose credit. Last thing, field lines will never, ever cross. They will never touch, they will never cross. This would imply a certain direction has two different values and directions for the electrostatic force. That's impossible. That shouldn't happen. If an object, or if an electric field had two different forces, you wouldn't be able to predict which way the object would go, and that's not what happens. We can always predict, or I shouldn't say go, we can always predict the direction of force. If you had two field lines crossed, that would imply that, hey, the force is going to be in this direction and in this direction. Well, that's impossible. Forces just have one direction. That's not the same as splitting something into components. That's just taking a force and looking at different aspects of it. Forces point in one direction. You've never drawn a force vector that has two different directions, that doesn't happen, okay? So field lines cannot cross. When we come back, we're going to examine field lines for other distributions of charge.